Let's look at an example using the Poisson distribution. So in this example, we've got cars arriving at a certain intersection, and they arrive at an average rate of 2.5 cars per minute. Let's call that the number of cars that arrive in a given minute, x. Okay, so we say that the variable x is Poisson distributed with a mean of 2.5. So that's how we say that, right? X is a discrete variable Poisson distributed with a mean of 2.5. We want to know the probability that X equals 4. And so that probability is, well, according to the Poisson distribution, e to the negative 2.5 times 2.5 to the x to the fourth, right, to the number of successes or occurrences over 4 factorial. Okay, and that will give us our answer. Now this works out to be, you can do that on a calculator, works out to be about 0. Let's be correct here, about 0.1336. And you can use this directly, right, knowing the Poisson distribution formula, and you should know that formula. You should be expected that I might hold you accountable for that. But you can also do this on the calculator, and so let's take a look at that. Your calculator has, under the distribution menu, Poisson PDF and Poisson CDF, just like we saw for the binomial distribution. In this case, we want a particular value for the probability number of successes, and so we're going to use Poisson PDF, and it'll ask you what's our lambda, or our expected value, which is 2.5. What's the number of successes? 4. Paste it, enter, and you can see we get the same thing as if we did the formula, 0.1336. And so there we go. We can confirm that we did that correctly. Part B says, what's the probability of exactly 4 cars in 2 minutes? Right. So the first part was 4 cars in 1 minute, and the second part is 4 cars in 2 minutes. Now the interesting thing about this question is that our average rate was given to us in terms of single minutes, but now we're being asked about 2 minutes. And so what's the right thing to do here? The right thing to do is to adjust our mean, or our expected value, our lambda, to the new amount of time. That is the worst lambda of all time. So to the new amount of time. Now the new amount of time is 2 minutes, and so if 2.5 cars on average arrive per minute, then in 2 minutes on average we would double that, and we'd have 5 cars per 2 minutes, right? So our new lambda is 5 cars per 2 minutes. So it's as though we've adjusted our units of time from 1 minute to 2 minutes. So now our new lambda is 5. And so again, x is a Poisson distributed variable. Tilde just means follows a distribution. The new mean, because we're dealing with 2 minutes, is 5. And so the probability that x is 4 is the exact same thing, only replacing the lambda with 5 instead of 2.5. So there we go. One somewhat common mistake that people tend to make in this kind of situation is to adjust in the wrong direction. And what I mean by that is, we could have thought, well, the probability of exactly 4 cars arriving in 2 minutes sounds like the same to me as the probability of 2 cars arriving in 1 minute. Right? So I'm adjusting the time unit down to the original unit of the rate, right? So if we work this out, let's just do that real quick so we get a number. We're going to get Poisson PDF 5 for, we get about 17.5%, about 0.1755. But if we do this, right, we say 4 cars in 2 minutes, that's like 2 cars in 1 minute. Well, now I've gone and said this is Poisson distributed with the mean still 2.5, and I want to know the probability of 2 successes. Well, what's that? If we look at that, do we get the same thing? So again, I'm going to say now the original lambda, the original expected value, but 2 cars in that minute. And I might think that's the same, but it's not. It's much higher, right? Over 25%. So what's wrong with this? Why is it the case that when I adjust the lambda to match my time, I get one answer, but when I adjust my time down to match my lambda, I get a different answer, right? This was, about 25%. About 25%, which is too much. Well, the reason those are different and why this one is actually wrong is that 4 cars in 2 minutes can happen in different ways than just 2 cars in 1 minute. I might have 4 cars come all in the first minute, or all 4 cars in the second minute, or 3 cars in the first minute and 1 car in the second minute. And this doesn't really account for that, right? 2 cars in 1 minute is just that, right? The 2 cars happen in 1 minute, and I would want that to happen twice, right? So if I were really doing this, I would say, oh, well, 2 cars in 1 minute, but twice, and so I'd have to sort of square that, right? 1/4 times 1/4 times 1/4 is 1/16, which is 0.16 something or other, right? 0.16 repeating, and so that's actually less than this, right? Because of what I just said. This can happen. 4 cars in 2 minutes can happen in more ways than just 2 cars in 2 cars, right? That's just one possibility. Now, it might be the most likely possibility, but it's just one possibility, and so those probabilities don't match up. And so when we're doing a Poisson problem and your lambda doesn't match, the time frame that you have, or that denominator doesn't match exactly, and you need to scale up your lambda or scale down your lambda to match that, rather than sort of thinking about that the other way, changing the parameters of the problem itself. Okay, so that's just a kind of a gotcha. Watch out for that. That's an easy mistake to make. So we used the Poisson distribution, or we learned about, or we derived the Poisson distribution from the binomial distribution. And because of that, we can actually use the Poisson distribution as an approximation to the binomial distribution. So, remember, Poisson is e to the negative lambda times lambda to the x, or x factorial, and binomial is, n choose r times p to the r, and 1 minus p to the n minus r. And so we can do that. The rules about that are that n must be large. Okay, n was the number of trials, so again, like the number of opportunities, and that the probability of quote-unquote success must be small, such that the expected value, or NP, is less than or equal to 5. These are just kind of rules that have been set up and accepted as to when you can use a Poisson as an approximation to binomial. You might find slightly different rules depending on what books you look at or what sources, but this all stems from the fact that the Poisson was found by taking n to be approaching infinity, so we want n to be large, and that the event is relatively rare. And so we want to remember when we're doing that, if we're trying to approximate a binomial distribution with a Poisson distribution, that lambda is mu, and that's the NP. So when we know NP, that becomes the lambda. Okay. So yeah. Let's look at another example. The probability of a person having a certain disease is 1.2%. What's the probability that no one has the disease in a random sample of 100 people? Well, we look at this and say, oh, 1.2%, that's like a constant probability of success, where success is this twisted notion of having a disease, right? So I successfully have the disease at a rate of 1.2%, right? But that's a binomial situation, right? If we think that this is an unchanging probability. And so ideally, I might be using a binomial distribution here, right? I might say, oh, well, that's like, 100, choose 0 times 0.012 to the to the 0th times 1 minus that to the 100th. Okay. That would be sort of the right binomial approach. If we want to approximate this with a Poisson, we realize that 1.2% is like 1.2 people out of every 100, right? So the rate is 1.2 out of 100. That's our mean, that's our average, that's our lambda, right? Our expected value is 1.2 out of 100. And so the lambda here would be the Poisson distribution would be e to the negative lambda times lambda to the 0th over 0 factorial, right? Remember, this is the number of successes, okay? And so, 1.2 to the 0 is 1, and 0 factorial is also 1, so this is just e to the negative 1.2. And maybe you're seeing, if you didn't already ask yourself the question, why would I want to use a Poisson distribution to approximate the binomial distribution? Nowadays, maybe you wouldn't. But before calculators, trying to do 1 minus 0.12 to the 100th power might have been something of a challenge. But I can do some things here that are a little bit less calculation intensive by doing things like Taylor series on E, for instance. And so I can calculate this potentially in a little bit easier way than this in a lot of cases. And so that's why we might want to approximate a binomial with a Poisson. Nowadays, we have computers and calculators that can do this very simply, so maybe we wouldn't want to do that anymore, but historically that's where that comes from. Let's compare these two values and see what we get. So e to the negative 1.2 is whatever it is. Negative 1.2.301. We can double check, right? We can make sure that we're getting the right thing. I said that's a Poisson distribution where the mean is 1.2 people per 100 and the x value is 0. And we paste that and we get the exact same value. So this is 0.3012-ish. And we can look at the binomial distribution as well, the binomial PDF, where we have 100 trials and a probability of success of 0.012, and we want no successes, and we paste that, and we get about 0.299. So you can see that's pretty close, 0.299. We're about a couple thousandths off there. So that's a pretty close approximation, and that's the kind of thing that we're talking about. So there you go. The other thing you can do with this is, let's say we have separately, we've got a town, right? And it turns out that, 5 people in this town have this disease, right? And we want to know, well, how likely is that if the probability of the disease is really only 1.2%? Maybe something weird's going on with this town, or maybe that's just not that unusual. Well, we can find the Poisson distribution of with a lambda of 1.2, but a number of successes of 5 or more, right? So I want to know, I've got this town of 5 people. What's the likelihood, not just of exactly 5, because that might be kind of rare, but what's the likelihood that at least 5 people have this disease, right? Well, this 5 or more, or at least 5, that is when we want to use a cumulative density function, the Poisson CDF. So in this case, we would want to use a Poisson CDF. So I wanted to show you that case. If we do that over here, second distribution, letter D, lambda 1.2 out of 100. We've got a town that has 5, let's say a group of 100 people, I should say, a town of 100 people. If it were a larger town, we'd have to adjust the lambda to match that, but let's say it's a town of 100 people, and we want 5 or more. Well, the CDF function calculates 0 through this value. Now, if I put a 5 in here, it's going to tell me the probability of up to and including 5 sick people. Well, I want to know greater than or equal to 5. So I'm going to calculate the CDF from 0 to 4 and then subtract that from 1. So we're going to paste that. We get this. 1 minus that answer is 0.77%. Pretty small, pretty unlikely. So maybe there's something in that environment that's causing that disease to happen, right? But in this case, this would be again like a 1 minus the Poisson CDF. You can see here 1.2 comma 5. Excuse me, 1.2 comma 4, because I up to and including 4. Okay, so this is the probability of more than 5 or more sick people. So there you have it. There are a couple examples for you. Look at the worksheet and try to do those as well. And if you have questions, feel free to email me. I'll try to answer you over email. Otherwise, I'll see you next week. Thanks.